All right, Nick, you want to go ahead and try sharing your slides and then we'll get going.
Certainly. Are the slides coming through?
Yeah, it looks good. All right, let's wait a minute more. I'm starting to admit people from the waiting room here. Okay, a couple more in. All right, I think we can go ahead and get started. We have a good crowd now. So we're pleased to have Nik Sultana from Fermilab, LBNL, and Illinois Tech talk to us today about some disclosure control and how you do the measurements and queries. So Nick, you want to take it away?
Sure, yeah. Hello, everybody. Thank you for coming to this talk, and thank you, David, for hosting. It's great to see so many familiar faces. Should you have any questions at any point, feel free to drop them into the chat or raise your hand if that's more convenient for you. There's no need to wait until the end or until the checkpoint. I'll be on the lookout in case anybody has any questions they want to raise during this. The topic of today's talk is very close to my heart, and I know it's very close to the hearts of various people in the school and in our community. And for the benefit of everybody present, I won't assume much in terms of context or background, right? I'm going to introduce everything piecemeal. So if you know some of this, bear with me until I get to the kind of the newer parts of this presentation. So my starting point for this research was another research project that some students and I had run, and that's still ongoing. And this is consists of a tool and a survey of the fabric testbed. So this involved creating some new infrastructure that runs on this testbed on fabric, but it runs kind of in user space rather than in kernel space. So there were some challenges to overcome there that made it the research more interesting. But and it's still ongoing in the sense that now it virtually runs itself. So there's a couple of cron jobs, and every couple of days they do kind of a scan, and they run a multi-hour job where they sample data, packets from this infrastructure, and then put it through a pipeline to analyze and graph it. And we populate a dashboard. So you can see the dashboard on the right of the slides. If you go to the URL that's backed by that backs that QR code, that'll take you to the project page that links to the dashboard. So in the course of this, there were two things that were impressed upon me. One was the timescales that were needed to gain access to the data, right? So aside from the risks that you have to undertake whenever doing research, right, because you're working with a problem that has not been solved, even if it's kind of a relatively well understood problem, such as network monitoring, there are still going to be elements of it that are going to be new, and especially if you're building systems, right? It always takes time to get to the point of building and validating systems. So that was one aspect. And another aspect was the difficulty then around what is it that you can share with third parties, with the rest of the research community, because we obviously want to make sure that the access to this data is being respected and it's being managed duly. So I think that kind of got me thinking around what is a research component to this, right? Obviously, it's a practical problem and it's a logistical problem. It's a well understood problem. In that sense, it's not a new problem. But that got me thinking along a path that identified research objectives that I'll spell out in this talk, and that I'll describe how these were overcome and what are the consequences of that. So the basic context of all this relates to network measurements, and um, you know, everybody on this talk would be familiar with the various types of network measurements that we might want to make, right? So just for the sake of completeness, I've put together a slide that kind of gives kind of different categories of measurements and specific examples of measurements that we might want to carry out. For example, relating to the utilization of the network, to the occurrence of different types of protocols, because maybe there is some kind of baseline that we expect to be normal, or maybe there is some pattern that might be abnormal that we want to look out for. Uh, we have inter-packet relations. So if we understand the dynamics of certain protocols, we can have measurements that scope out whether the connection looks healthy or not, right? So if we see things like retransmissions, right, that relies on knowing some context about the protocol and what came before in order to determine whether it is behaving anomalously that might indicate congestion or a misbehaving endpoint, right? So that's all kind of information that we might gather from measurements through carrying out these observations. We have node occurrences, right, and the topology of a network. And then finally, I've put kind of together as flows as a separate abstraction, right? So these kind of categories aren't independent of each other. They kind of correlate to each other, and you know, as we move into higher numbers, they kind of you reuse features from the lower numbers of measurements that I've identified. By no means is this a complete list, right? This is just a set of examples that I gleaned from a bunch of papers and from speaking to people as being an example of the kind of stuff that people care about when they measure a network. All right. So as we know, we go about measurements by instrumenting the network, and typically this relies on the capabilities of hardware in order to try to ensure that the instrumentation doesn't get in the way of actually doing productive work. So instrumentation kind of it decomposes into three types of outputs that are produced, right? There are flow records, there's interface records, and then there's packet captures, which is arguably kind of the richest source of information you can obtain, but also it is the information that comes at highest overhead to obtain. And this is what patchwork kind of derives, right? So it uses port mirroring, right? So it exploits with the operator's permission, obviously, it uses the span port feature in order to sample the data plane of the test port. Now, coupled with all of this, there's obviously kind of active approaches that people can undertake. And indeed, one kind of an observation is often people have to take active measures because kind of measurement approaches because kind of passively obtained measurements might be more difficult to obtain. And this goes back kind of to the motivation for this research, right? There is a certain inertia. It's well reasoned and kind of well-meaning inertia around sharing data. But I believe that there is a technical kind of research-based angle that can help reduce that inertia. That is what the subject of this talk is. So I'm more going to be talking about kind of the passive style measurements and how to facilitate the sharing of those. So key thing that's missing in all of this is specifically what is it in measurements that we allow to be disclosed, right? So since we can't express that, we can't really control for that. And I'll explain a bit more about what I mean by the disclosure control, right? So the reason we want to control disclosure is well understood, by everyone at this point, right? So there is a certain sensitivity around sharing data that's in the network because of the users of the network as well as the operators of the network. And however, we can't, without having a kind of a more crystallized idea of what it is that we don't want to share, we can't really take a very surgical approach to protecting that, right? So usually we take other measures in order to manage disclosure. So the measures we take consist of oftentimes some degree of anonymization of data. Now, this has a very kind of, well, a somewhat troubled history, I would say, in the sense that um, it is not the only tool you want to have in your toolbox, right? There's various examples going back decades that show that anonymization doesn't always result in anonymized data, right? Or at least not anonymized to the extent that we'd like. So something that's a bit more recent. It's been the idea has been around for 20 or so years, is that of differential privacy. But differential privacy kind of targets the output of a kind of a statistical table, and also it is not entirely a perfect fit for this problem because it doesn't exploit the structure of the data that we are measuring, right? So network involves dealing with structured data, right? Think of packet formats or flow tables, right? Uh, SNMP blocks, right? So there is a certain structure to that, and the focus, the kind of parameters that we can change, we can alter, the knobs, we can turn differential privacy tend to be a lot more coarse-grained. So there quite a few tools have been developed, mostly around the first idea, right? So for anonymization, here I've captured several. I'd like to capture more. If you were associated with a tool that doesn't show up here, my apologies. I tried to kind of sample the kind of the features that seem most salient. Feel free to email me to point out anything missing here. And I have also tried to reduce this to like key ideas that the tools introduced when they came out. So out of these tools, I've identified two in particular. And again, it's not to say that the others, are less meritorious. It's just that these two kind of stood out in terms of the innovation they brought and the ideas they brought and the influence that they had on other tools. So the two I'm singling out here are TCP dpriv and TCP make pub. And the kind of TCP dpriv is, so many of you will be familiar with with this tool, right? It allows for kind of configurable randomization around addresses and ports. And TCP make pub introduces a notion of anonymization policies and also some degree of validation around those policies. In other words, how do you know that your policy is working? So kind of, I'm going to draw some kind of sharp contrasts between existing work and past work and kind of the topic of this presentation. So one observation I would make is that the LBNL has had quite a substantial impact in this particular field, right? So you see a lot of papers and tools that either from there or affiliated with LBNL or that cite datasets from LBNL. Another observation I would make is that a lot of the focus in existing tools is on anonymization and some degree on randomization. I tend to think of this problem more as disclosure management or disclosure control. And I think that there is kind of a subtle but meaningful difference, or maybe not so subtle, depending on how you approach it, in the sense that you can choose whether something is going to be disclosed or not. Whether something is anonymized or not is kind of a function of the context in which that data finds itself. So I'm going to focus more on the disclosure part. I'm going to argue that it can enable anonymization, but I think it's very tricky to try to get to anonymization in one bound. And also, anonymization is, as I mentioned, in my mind, a function of its context, right? So it's not always something that can be guaranteed. A lot of the time, the tools, they look to reconstitute pcap files. So that in the tool I present in this talk, you could do that, but I'm also looking to kind of generate other types of data where you don't have a structure that resembles a packet. What I'd like to do is have data that is derived from what you find in packets, but whose disclosure is managed in a way that I'll make precise in this talk. The tools, they eventually they move towards allowing a lot more flexibility when it comes to parsing and processing, right? You see this especially in this work here by Peng and Paxson, right, where using Bro/Zeek, right? So they provide a high level of language for describing kind of anonymization functions applied to fields in parsed packets, and going beyond the first few sets of headers, right, even up to kind of application formats. But in all of this, there still remains an open problem, which is the need for automatic and trustworthy validation/verification, right? So you still have to trust that the tool does what it claims to do. I'm going to come back to this because that's actually the key issue, right? So that's something that is really important to overcome. And so when working on this. So what's the state of the art today when sharing data? So the state of the art combines of using a tool like one of the ones I've just mentioned, or one that is derivative, but also coupling that with an agreement between the source and the recipient of the data, that the data is going to be used certain ways and it is not going to be abused in specific ways, right? So I'll say a bit more about what this means. But I will point out that this approach is extremely successful. It has led to the sharing of a lot more data under this scheme, right? And you find it being employed by various data repositories. So now I'd like to kind of point out why, at the moment, we don't necessarily live in the best of all possible worlds when it comes to data sharing, right? And this is where I'm going to go towards a technical solution to a problem that is not only technical. So one problem that we have is that the agreement under which data is typically shared is very difficult to enforce, right? So you can't really detect or prevent the type of activities that the agreement is set up to prevent, right? At least get an agreement from a party that they won't carry out. Typically, that involves the party agreeing not to share the data onwards and also not to attempt to de-anonymize the data. Also, agreements are coarsely defined, right? So as an agreement, the two parties are agreeing on supplying the data and on using the data within certain conditions, maybe in a certain location over a certain amount of time, but also, they're agreeing not to do certain activities. I would like to contrast this with thinking about the recipient being unable rather than unwilling to carry out certain activities, or only able to carry out certain activities conditional upon other features, such as on certain types of packets, right? So or on the context of a packet stream. So this is something that we could formalize, and in a few slides I'll tell you how I go about it. But currently we don't. Also, an agreement such as a DOA is typically drawn up by attorneys. That is expensive to set up. It is expensive to change, and it is typically not catered per user, right? So by no means this is kind of like uniformly the case, but by and large, you have when data is shared, it is going to be the same data that's being shared under the same agreement with other researchers. So this goes both for the agreement as well as for the data. And the data is usually pre-processed for that anonymization goal I mentioned earlier. And this is something that is coupled with what the data consists of, right? So if you happen to have a novel protocol, then you have to modify the part of the code that does the dissecting of protocols in order to make sure that no addresses make it through this little protocol too. Which for in research contexts provides a bit of a tension, right? Because you might well have, IETF, standardized protocols that show up in data sets, but you might also have, on an environment like Fabric, for example, protocols that researchers are only prototyping. Okay, so the core of this problem, right, if we were to kind of try to boil it down to its essence, it's one of trust, right? Going back to the point made earlier, trusting that the data won't be abused by its recipient, but also that the data can't be abused, right? This is the point where we haven't reached just yet with current approaches. And this reluctance from speaking to people, it has kind of been internalized culturally, right? So people tend to be very conservative around sharing data, and that's understandable given the run up to this, right? But it does have the effect of being biased more towards not sharing data, right? Because it minimizes risks. And something that is for us working in more research-facing environments, something that is important to always keep in mind is that the safest choice is not always the best choice, right? So limiting options in terms of sharing data that could enable new discoveries. If there's something that we can do about that, then we absolutely should. Okay, so based on everything I've said so far, what does this break down to? What are the research problems I see? So one problem is how to express disclosure policies. And I'll be a bit more precise about what I mean by this and give you an example of such a policy. So once we have policies, we need to be able to reason with their measurement satisfies a policy, right? Or with the measurements, the data that would be gathered by the measurement would violate the policy by disclosing information that the source of the data does not wish to be disclosed. And then we need to make sure that people trust that the system works. In particular, the source of the data needs to trust that only data that is allowed by the data disclosure policy can be disclosed. So how does this map to research objectives? What did I build? So one key idea here is using eBPF to express network measurements. This in itself is not a very controversial or new idea, right? So eBPF has been used for various objectives. For those of you unfamiliar with it, I'll give a quick one-slide intro to eBPF soon. So it's a very kind of proximal idea to use eBPF to encode network measurements. What I propose that's novel here is also using eBPF to encode disclosure policies. So you can have an eBPF program that is in itself encoding a sort of a contract. And then we define a formal semantics, right, a precise meaning for disclosure policies encoded in eBPF. Having a precise meaning means that we can then offload the reasoning to mature tools that do automated reasoning. Now, mature here is also a byword for trustworthy to some extent, but not to the full extent, right? So to get to the fuller extent, what I'm proposing is having this process work in an evidential way so that were any of these tools to have bugs, then it is easier to catch that sooner rather than later, right? So part of this, you can think of it informally as who watches the watchers, right? If you have some kind of reference monitor that's deciding yay or nay as far as whether a measurement query is allowed under disclosure policy, then this approach is providing you with more leverage in order to find out whether a program might have miscalculated. And I'll give some more context as I go along. And should you require more information, feel free to ask. So first, let me give you some more context on eBPF. Um, so originally, it started out in part when investigating congestion collapse of the internet quite a while back, and then in 1997, BPF, which is this 8502 inspired kind of assembly, got mainlined into the Linux kernel. And one appealing feature is that the language has limited expressiveness, so that you can't have packet filters cause the kernel to diverge, to crash. And the other is that there is a kind of a software check to help enforce this, right, to the verifier. And then a decade ago, it was generalized. That's how we got to eBPF, right? Extended BPF. And it's rather displaced other features like dtrace, right? So there were and still are excellent alternatives when it comes to host level monitoring, but eBPF arguably kind of went from packet filtering to a more extended model that has been applied to the kernel, to user space, and to beyond, to an extent that the dtrace did not, right? And maybe one could argue that the Linux approach and the Linux footprint versus the Sonos and or Solaris and BSD footprint might have had something to do with that. But in any case, I see eBPF as a means to an end for the goals of this work. And something else I mentioned is that it is work in progress, right? So eBPF started out kind of working within the context of the host, but it is not necessarily applied within the context of the host, right? So here I kind of abuse the context so that it's applied within the network. So what I mean by using eBPF to encode network measurements is to use the eBPF language. I'll show you a snippet of that soon, to encode a measurement function that's going to be applied to packets as they come in. And then it's going to make calculations and then call some external functions that are going to maybe post-process and ultimately store the results of these functions. So what we have is packet stream, and then we have a function run by eBPF, and then we get some measurement result. And I'll give you next an example of two of the measurements from the table that came earlier. Right, so one is basically a count of packets, right? This is as simple as it gets. And the next is a count of packets that's sensitive to parsing, looking for a particular protocol. So this is what it looks like. Here you can see on the right, we don't have kind of persistent memory that we can use directly in the language. We can get persistent memory by using kind of extensions of the language. I'm sidestepping here some details that differ between BPF and eBPF, right? And also talking about associative storage. But think of this as a call we can make to an operator-provided function that can give us in a register the value that has accrued so far. Then we're going to move it to another register. We're going to increment that. So from R0 to R1, right? Because the return call of the function comes to R0, goes to R1, increment that, and then we're going to pass it to this other function. That's M1. M3 is lines 6 to 11, where we're going to here we're assuming Ethernet, we're reading the ether type, and then based on it being IPv6, it will apply the same idiom that we saw on lines 1 to 4. Okay, if it's not IPv6, then to just jump in and continue. So this is the way I prefer to write eBPF in terms of kind of its assembly notation. There are higher level ways to write it. I partly prefer this approach because this allows you to see also why eBPF can be complicated. So before I get to complexity, I want to show you kind of a bit more its flexibility, right? So you can see how you can apply these ideas, these idioms, to have it work with pretty much any packet format, right? Any header format and any encapsulation of headers, because um, you can concatenate code that is progressively going to parse through packets. And you can copy, for example, in this case, a source IPv4 address and store it. Or you might opt to pick only the 8 bits, right? The topmost 8 bits of the IPv4 address if your policy requires you to be less detailed, right? Not to capture the full address. So now, I mean, I think it's reasonable to see why eBPF is very powerful and expressive for parts of what we want to do, that is to encode network measurements. But how do we know that those measurements are indeed doing what we think they're doing? In other words, I'm moving towards how do we check those measurements against the policy, right? Because we can see that code can be complex, eBPF code can be complex, it can contain bugs, and it can be complex enough to encode side channels. So, by way of um, a distinction here is, there is verified code of the eBPF code that won't crash your kernel. That's fine, but we also want it to be correct in the sense that that I'll make it precise in a bit more, right? So we want to make sure that it is correct in the sense that it only allows measurements that are disclosable. So to give you a sense of complexity, note that you can write code that is itself encodes a distinction between what a packet contains. So here we have kind of explicit knowledge that R naught, right here, that the ether type has a certain value. And then based on that explicit knowledge, we can turn it into implicit knowledge based on the branch that the code takes. And we can write the topology, we can draw the topology, right, as having a property, and then have a branch in which the property is false and the branch in which the property is true. And we can branch forward and we combine the flow, right? So this is just an extension of the example I gave you previously, where we have some implicit knowledge that comes into the code, and then we're branching based on the property being true and false, and then they merge again and kind of they negate each other, right? So at I, we don't necessarily know whether we came through this through the P or to the not P approach. Anyway, this gets really complex, right? So even though eBPF is a relatively simple language, it can get pretty complex pretty fast. So the takeaway is that we don't want the human to be in this particular loop, right? We don't want to rely on humans to do this policy enforcement and policy checking. So a way we can think about automating this is by using an idea called information flow control, or you also find it as state analysis, where we have kind of like a virtual model of the eBPF architecture. And we reason about the explicit and implicit data flows that are taking place as this program executes, and abstracting away what data it is executing on, right? What packets it is executing. And there has been work that applies IFC to eBPF, but the work doesn't apply IFC in a way that helps us solve the problem of disclosure control, particularly because for disclosure control, we need to work with conditional disclosure control policies. I'll give you a precise example of this yet. There's also other gaps that need to be addressed. So the work I describe addresses all those gaps, but the conditional part is especially key. So what do I mean by conditional? Well, depending on what You might need or you might want only to allow the disclosure of information that depends on other information that exists within the packet, right? And that is the sense in which it is conditional. So, for example, here, if we have a particular ether type value and we want to allow a measurement to read, not necessarily store, but at least starting with read the IPv4 source address, well, that is going to have to depend on a particular value that comes before it. And we might, we have to encode that dependency somehow, right? Equivalently, might want to allow a measurement to read an IPv6 source address, but that's going to be at a different offset. So it's important to track these dependencies when reasoning about the program. Otherwise, we end up with very coarse-grained disclosure policies. You don't want to just always allow a certain offset within a frame to be readable because it's, whether it is readability or even meaningful, whether it's readable or even meaningful, depends on other features of the frame. Okay, so I'm going to get to showing you a demo soon, but kind of just to bring everything together of how this works is I'd like the operator, so the person or the entity describing the policy, to declare labels. They're going to label the contents of frames. They can have as many labels as they want. And they can use these labels to signify, for their own intuitive terms, the importance or the sensitivity of this information. And so labels are going to be mapped conditionally to offsets within the frame. And then there's going to be an API examples of which I showed earlier with like get count and store count, right? That the operator provides. So those are trusted functions by the operator that allow the transforming of labels so that you can have data that's allowed to be read from the packet, but then must be passed to one of these functions before its result is actually stored. Right? So that allows the operator to control the disclosure of information that originated from the packet. And finally, we want to ensure that this reasoning is preserved by the measurement, right? And so this comes back to one, policy enforcement, but two, how do we trust that the policy is actually being enforced? So before I get to the trust part and doing the policy enforcement part, I thought I'd first start by showing you an example of what a policy looks like in this domain. So this is a policy I wrote in eBPF that extends eBPF using these assembler directives, such as .label to declare labels, and transform to describe how functions, operator-provided functions, rely on being passed information that has a specific label and what is the result of that function. And then the policy is specified by selectively and progressively tainting offsets within a packet with certain labels. So in this case, for example, the ether type is being labeled with LRead, right, with label read. So this results in a kind of intuitively in this kind of this white square here, right? So LRead is we're using kind of just this white color to visually show this label. So that's the point where we've arrived at. So far, red means that it's unlabeled. So red is unreadable. And then depending on the value of what's at this offset, we can then conditionally taint with some other label, in this case, non-disclose. It can be read, but it can't directly be disclosed. The value at a certain offset. And we can see that in this case, we can go from a non-disclose to a disclose by calling the L1 function. And we can only store values that have this disclose label, but you can't materialize disclosable information. It must go through other functions that make it disclosable, right? And ultimately must originate from the packet. So in terms of the workflow, we start out with in this section here, right? So we have disclosure policy and the disclosure API that the operator puts together. The policy is then provided to a checker that, combined with a measurement query, is going to produce evidence of compliance. I'll tell you a bit more about that in a second. And also then input into the query executor that uses the disclosure API in order to execute. Once we've reached this point, stage 6, we can go through stage 7, where we can feed the executor packet stream, and we get to the last stage where we get disclosure safe measurement data. It's disclosure safe in the sense that it would have passed the policy and query checker, and also has produced 2 layers of additional data that attests to this. So this is so I've implemented all of this, and I'll tell you about kind of a pilot experiment. So the part of the deal here is that this needs to be trustworthy. So trustworthiness is partly derived through formal semantics, so having precise rules about what eBPF instructions mean in the context of measurements and policies. Also, note that this analysis is done statically, so no runtime overhead, right? We, like, us networking types, we're very sensitive to runtime as well as being sensitive to security, right? So here we're being conservative on both fronts, right? On the security front, by having this kind of defense in depth sort of idea for policy checking, as well as no dynamic overhead. And the way it works is by essentially looking at every possible execution of the program and every kind of policy allowed mapping of labels to the program, and ensuring that you never have an invocation of a function with the wrong labels. And this implies that you never returned the kind of a value that had a label from a function that is not being intended to be fed to a different function. You can think of it in terms of types, if you wish, right? That function it enforces a discipline of strict typing of strings. I could expand on this. These are examples that I explored of challenging the setup when annotations are missed, or when there is bugs in the program or in the policy, to check what happens when they are. In terms of implementation, so the tool is it works by producing a model from the policy that's encoded in eBPF, and the measurement program that's encoded in eBPF produces an encoding of that in so-called SMT, satisfiability modulo theories. This is like an extension of propositional logic that allows you to reason in specific additional domains. So I use that to make it more feasible to reason about the structured data formats that we use in networking. And also I built about over 2K log of eBPF of several tests in order to both positive and negative tests to put this through its paces. Now, in terms of what does it look like when it runs? So here's an example from regression suites. This is an eBPF program. It starts off with the policy. So we're having the read label saying that this offset can be read. Then we're reading from this offset, fair enough. And then we're reading from an offset that has not been blessed, right? So this is where we expect it to fail. And in the program that showed up on line 12, so we run the tool, and it's this error output is because the policy was not successful. So we see that it was unsatisfiable, and it is correctness underscore line 5. But what does it mean in the context of this intermediate model, right? So here you can see one of these intermediate models that are produced, that you can see that you can check that there are no bugs in my program, right? So we can see that line 5 relates to this second read that was not allowed by the policy. So this is an example of one of the shorter negative regression tests that I used to test this. I also have other kind of, I have a positive test to show you, but in the interest of time, let me get to that later. Because I want to tell you a bit about the pilot experiment. So in terms of research problems, the expressing of policy parts, I'm using eBPF for that, right? Augmented with the directives I mentioned. The reasoning and the enforcement parts are done through formal semantics, and the assurance comes from two parts, right? So one, we are encoding the problem for solution by a third-party mature tool, and then we're getting evidence from that party, that tool, with their, regardless of whether the policy check passed, or, as in the case that we just saw in the demo, the policy check failed, right? So we get to see exactly which part of the policy failed, or rather the query failed the problem. In terms of evaluation, I approach this in three ways. There's obviously kind of showing generality, right, by trying it on a bunch of examples and measuring size and time overheads. I also did proofs that the static semantics imply this kind of well-behaving kind of theory that this relies on, right? In other words, how do we know that even if the tools were to be perfect, how do we know that there isn't a bug in the theory, right, in the semantics? So that's what the meta theory is capturing. And the third part is a pilot experiment on Fabric. So for this pilot experiment, I'm building on the data on Patchwork. So that's the project that I talked about in the first slide. And the policy I set up is that I can disclose the occurrence of certain types of headers in the traffic. And in addition to that, I can read tags. I can read VLAN tags and MPLS labels, but I can't disclose their values, right? I can't tell you literally what the values were. I must put them to an aggregation function. So I'll give you an example of what this ends up looking like. And then for the IPv4 or IPv6 headers that I can disclose, I can read the next header field value or the protocol field at IPv4, and again pass it to an aggregation function. So then, in terms of measurements, what I'm doing is I want to compute the distribution of how frequently certain tags, how frequently tags occur, right? Without being specific to certain tags, and same with the protocol slash next header values. And what I get out of that is the count of these values. I'm not getting the addresses. Remember, I can't even read the addresses, right? Because the policy does not allow for that, right? It doesn't even label those offsets. And I can't get the specific values for these aggregated for the values that I can read. So what the graphs end up looking like is like this, right? So this is for IPv4 protocol, right? So this is for what is at layer 4, right? Without being specific about what precisely is at layer 4. But we can see kind of the relative occurrence for the data sets that we looked at. And this is the same for the VLAN tag, right? So we see a distribution of values. We don't know what specifically the values are. And the thinking here is that, one, we don't want users to rely on these values, or we don't want them to potentially abuse these values. So this is part of ongoing work, right? So one of the theses of this work is that you can have both flexibility and assurance. I put a lot of work into both because having just flexibility alone will not result in any uptake. And having assurance alone will also not result in any uptake, right? You need a bit of both. And the idea here is to give the assurance, particularly to the operators, and the flexibility to both operators and to the to stakeholders with whom the operators might wish to share data. And there is other ongoing work, right? So the focus of the stage was laying the foundations for the formal semantics and the tooling, right, to make sure that what we build on this is built on strong foundations. I understand that not everybody has, my appetite for writing assembly, right? So ongoing work leads to kind of a higher level approach to specifying the types of policies I showed you, as well as collaboration with other infrastructure operators beyond Fabric to test this with a wider variety of policies. And so one of the things I'd like to get, something I'd really appreciate from the community, is inputs related to this. So that QR code points to my webpage, which points to my email address in case we don't get to talk today. But I'd be especially interested in discussing data use agreements, and particularly any disclosure constraints that you face or that you'd like to overcome. And I have context for having worked on this for quite a while, on how to determine whether it can be shoehorned in this framework, or reasons why maybe it is the safest and best solutions might coincide in that case. I'm also interested in any particular, even customized network measurements that you're interested in. I can speak eBPF fluently, right? So we can customize that. Always interested in uptake, right, and understanding any practical, organizational, logistical obstructions people might face or perceive when it comes to undertaking this. I'll point out that you don't have to give me any data, right? So one modality that this enables is for you to run the tools on your own site, right? And in fact, that's something I encourage, because the operator must always be in control of what they might eventually disclose, right? So you don't have to have like a trusted third party or me to gatekeep on that. It is the operator, the source of the data, that makes those calls. And then finally, actually pre-finally, so in this talk, kind of I avoided kind of the maths and the logic parts of the formalization, because when I was discussing this with people, they said it looks, it's not the right tone. So I was wondering if there was any part of this presentation that you wished could go into more detail on certain aspects, or if we need less details on certain aspects, because it spans across networking and systems and privacy and formal methods, right? And it's a bit tricky to get the balance right for different audiences. So I'm always, interested in hearing about how this can be better calibrated. And then finally, if there's other problems that this approach could help with, right? So particularly this mix of trying to build trustworthy tools, right? So having a technical solution as a component within a problem that is not entirely technical, right? Because as I said at the beginning, part of the reason we don't share data isn't because we don't necessarily have the tools to do that, right? But it's also because we haven't come across ways of trusting the tools that we have so far. So with that, I'll stop, and we have a few minutes for questions, I think.
Nik, great talk. So thanks for going through all that and showing examples, I think was really helpful. So we have a few minutes for questions. Do people have any questions they want to bring up? Just feel free to unmute yourself and ask. I'll check the chat as well, but cool. Scott, did you have a question, or there was just the comment in the chat?
Just the comment in the chat. It's really interesting to learn more about eBPF.
Yeah, so Nik, I have one for you. So have you, AI now is taking over all of the pain of writing code. You think it can take over all the pain of eBPF? I can't even say it right. So
Um, I yeah, it could take over some, it's first of all, I mean, I'll point out that it's not pain for everyone, right? So, but in the sense that I love the kind of the conceptual simplicity of certain programming paradigms. eBPF is one such example of a member of. But what I worry about with AI is that it might introduce new types of unknown and sudden pain when it comes to reviewing the code, right? And as especially if that code ends up being complex, complex systems fail in complex ways, and so that can create kind of, especially since a key part of the problem here is trust, right? It becomes very difficult to trust that the model is untainted and that what the model creates is both efficient and safe to use. So maybe, but that's still work in progress. I have I think of it as, how like when we fly in an airline, right, there are two pilots who are guiding this, and we have a shared interest in everybody making it to the destination safely. With an AI, I feel kind of a little bit of alienation in the sense that we don't necessarily literally have skin in the game, right? So I would much rather, a fellow human be entrusted with that, as it were.
I understand. Well, it seems also like AI could maybe de-anonymize some of this unless you come up with a more complex scheme than you have right now.
That's a great point. Yeah. So maybe it can play an adversarial kind of red team sort of role. And there, if it fails to de-anonymize, it doesn't mean that it can't be de-anonymized. But if it succeeds in
Right,
de-anonymizing,
right,
then that would be pretty good evidence to go on.
right. Good. Do we have other questions before we close down the call and thank Nik? Cool. All right. Well, we'll give you a round of virtual applause and thank you for putting together a good talk and taking the time with us.
Thank
And
you. Thanks,
we'll
everybody.
we'll see you all later.